All right, welcome everybody. Thank you so much for joining today. We're here with the team from StoVentec. We've got Kate and Brock on today. They're going to be giving today's AIA CEU approved course on Rainscreens. We were just having a great conversation where we were talking about how there's a lot of debate and confusion around like what even is a Rainscreen. So today is going to be a really awesome opportunity to learn a lot about Rainscreens and how they work. Kate's super knowledgeable. She's going to be giving the presentation, and we've got Brock on today to help out with some questions. So really want to encourage folks to submit questions to the Q&A throughout today's presentation. We'll have some time to get to them at the end, and if we don't get to your question, we'll have a record of it so we can follow up after today's event. A few housekeeping items from me, and then I'm going to pass it over to my colleague Helen to give a quick little intro while folks are still joining about Acelab and show you how to get in touch with today's presenters directly on Acelab. But first off, just want to mention for AIA CEU credits, we did ask for AIA numbers upon registration. I'll also send over a form in the chat in a moment in case you're concerned that you didn't include it. You can submit it to us there as well. All right. With that, I would love to pass it over to Helen to give a quick little intro about Acelab, show you how to get in touch with today's presenters, and then we can go ahead and get started with today's CEU approved course.
Awesome. Can you all see my screen?
Yep.
Thank you, Bo. Yes, so I'm Helen. I'm the Director of Architect Experience here at Acelab, and my job is to essentially support all you architects that are joining today, making sure you're having a great experience on the platform. As Bo was mentioning, we were talking earlier about what is a rain screen. Just a quick note for y'all, when you're looking for rain screens within Acelab, for the most part, you'll go to Products here and then select Cladding. So speaking of this, I want to talk a little bit about ways you can use Acelab, and then I'll wrap up with kind of how you can get in touch with these lovely folks. So I'm going to jump into the workspace here. I'm going to jump into projects really quickly, and I'm going to scroll down to an example of how you can use Acelab. We're setting this up as a firm library. So this is a spot where y'all can save all of your products that you use frequently and allow your whole team to jump in and collaborate. As we're talking about Rainscreen/cladding, we're going to jump in, just going to show y'all here a couple different things. So within this, you're able to leave comments. So your entire team can come in, you can kind of create that knowledge sharing collaborative tool here. So if somebody happens to go out on maternity, paternity leave, someone's sick, someone, moves on to a different firm, all that knowledge of how this product works can live on within your firm by using these kinds of comments. The other thing you can do here is you can always directly contact the product reps. So I'm going to show you how to do that for Sto. You're going to come up to the top, type in the brand, select brand here, and then we're going to jump into their page. And what you'll see here is lovely Brock. So if y'all have any questions, you can contact him. That'll create a message within your workspace here. You'll get an email notification about that when he responds. And then you can also check out all of their amazing products here that I know a lot of folks are really interested in and excited to use. So all that being said, that's one way that we can kind of use Acelab as a spot for y'all to store all of your material research, kind of keep that knowledge sharing going, connect with these folks directly. Last but not least, I want to talk a little bit about this live chat option. And if you don't find something that you want, we want to hear about it. And here's just one example of somebody who's looking for aluminum windows. You can live chat us, and basically our team was able to make these recommendations for folks. So we can do this for you as well. If you ever have too many options, you're not sure what to do, we're here to help. And this is all free for y'all to use. So I will turn it back to the wonderful folks at Sto to talk a little bit more about all these things. Thank y'all.
Awesome. Thanks so much, Helen. All right. I just launched a poll, so if you're interested in learning some more, feel free to fill out that poll. We'll also drop Helen's meeting link in the chat so you can book a free 15-minute session with her to learn some more about Acelab. All right. With that, I'd love to pass it over to Kate. Whenever you're ready, Kate, feel free to get started with today's CEU approved course.
Okay, thanks so much. Resume sharing. Can everyone see that?
Yes.
Okay, great. Just a quick introduction. Hi, my name is Kate. I am the Rainscreen specialist for StoVentec based in the Northeast. I'm actually based out of the New York metro area. Brock, can you pop on for just a split second just to introduce yourself?
Yeah. Good afternoon, everyone. Brock Osborne. I'm based in Richmond, Virginia, and cover the Mid-Atlantic states for Sto Corp and the Ventec program.
Thanks, Brock. And then we have another counterpart down south, Justin Webb. We basically between the three of us, we cover the entire country for Rainscreen systems and some international projects as well. So as and when you need assistance, just reach out to any of us. We'll point you in the right direction and get you the help that you need and the support that you need. My contact information is available to you on the Acelab platform anytime you would like it, as well as Brock's. So today's presentation is Rainscreen systems in the building code. We're going to start with kind of an overview and then get a little bit more granular as we go through. So if there's a question that kind of pops into your head about something specific that we're covering in the beginning of the presentation, odds are we might cover it later on. Just a couple housekeeping items for the AIA. We've been requested in the past to send out the slide deck. The AIA is not in favor of that practice. However, you will see that there are slide numbers on each and every slide that we have in the deck. So if there's a specific wall section detail or some additional information that you'd like, just jot that slide number down. You can email us afterwards or contact us through the Acelab platform, and we'll be able to send you more information on some of what you saw. So from this point forward, because this is an AIA accredited presentation, I am going to refrain from using any branded language. I'm going to try and remain as agnostic as possible, and we're going to keep to just straight educational content. And when we get to the end, if you have brand specific questions or additional follow-up questions on any of the technical information that you've seen throughout the presentation, we'll get to those. So let's jump right in. So our four learning objectives for today. First, we're going to do that 30,000 foot view that I mentioned of Rainscreen. We're just going to provide a general overview of the control and system layers. We're going to talk a little bit about the history and really define that term for you because there is a lot of confusion around it. Then we're going to get into some of the building code and testing that are relevant to the building envelope generally. Then we'll get into the intersection between Rainscreen systems and those testing parameters and building codes. And then finally, we'll kind of walk through the spec process and see what that looks like for our design community. So we'll jump into learning objective 1. So first, there's a lot of confusion about Rainscreen. We mentioned we were having a side conversation before everybody logged on about what exactly is the Rainscreen, where is it found, in what division of the specifications, what is it? So there's an organization that was formed in the beginning of 2020 called the Rainscreen Association in North America, and they had the same confusion that you probably do, and they wanted to clear some of that up. So they went ahead and defined Rainscreen for us, and they describe it as an assembly applied to an exterior wall, which consists of, at a minimum, an outer layer, an inner layer, and a cavity between the two, sufficient for removal of liquid water and water vapor. It's been incorrectly defined as a single exterior building skin material. That's your cladding or your facade, and you will find a lot of Rainscreen systems kind of housed within cladding because it is the part of the system that you see. Then a collection of individual components aimed at functioning as a system. That is what we call a Frankenstein system. It's commonly how Rainscreen is specified here in the US today. It's a manufacturer that's been selected for their cladding, and then another one for their subconstruction, and then another one for fasteners, and somebody else for the waterproofing, and someone for the insulation. And you kind of cobble all of those manufacturers together and hope that it performs the way you intend it to. And then the final one is it's a building science principle. This is the one that resonates most with me. It's not one manufacturer or 10 manufacturers. It's not one component. It is the concept of creating an assembly on the exterior wall that consists of the outer layer and inner layer and a cavity between them. And that cavity is really the secret sauce. And then because it's not complicated enough, we have 2 different kinds of Rainscreen systems, and there are classification tests for these systems. We have the AMA 508 and the AMA 509. The 508 is for a pressure equalized Rainscreen system. Your 509 is for a drained and back ventilated system. So just to give you an idea of this classification test, there were a lot of tests out in the universe that looked at wind loads, they looked at water penetration, but none of them really measured drainage and drying and airflow, actual physical airflow behind that cladding. These tests do measure that. So it's not just, some manufacturer reps saying, yeah, we have airflow back there. There's a lot of drainage back there. It's a test. Like we've tested this, we've measured it. There really is airflow and convection going on behind cladding. Your drain and back ventilated relies on unrestricted air movement to drain and dry the wall cavities. Sometimes those are referred to as open joint systems, but basically we have unmitigated air movement across the wall. Your pressure equalized was born out of the need to kind of mitigate some of the wind loading going on buildings, particularly when we're doing metal panel on very tall buildings. We have excessive wind loading near the top of the building. Those panels are very light and aerodynamic. We don't want them winched off the wall and going airborne. It's very dangerous. So we introduced this idea of air dams and other drainable compartments to kind of carve the wall into lots of little rain screen systems. Just to move on to the functions of a rain screen, we like to refer to them, our marketing team likes to refer to them as the 3D principle. We want to deflect, drain, and dry. So we're always going to have water management, because if you don't have a ventilation cavity, you do not have a rain screen. Structural integrity is going to be a function of what cladding you select, and different types of claddings are going to have different impact resistance. We'll talk about that when we get into the testing, as well as your fastening schedule. We're also going to talk about that a little later down the line, but that sub-construction schedule, that fastening pattern, that's going to dictate a lot of your cost. Energy conservation is we're using continuous insulation, and ideally our sub-construction is thermally broken in some way, so we don't have excessive thermal bridging. We're going to get into detail on all of that too. And then finally, fire protection. That includes fire blocking details and full assembly testing. Because we are talking rain screen today, we are only dealing with non-combustible insulation, because we are riding directly adjacent to a pretty sizable air gap. So why pick a rain screen? Probably the top reason is aesthetics, at least on the design side. Usually you're not going to find a plumb wall, whether it's aging construction that we're reskinning or new construction. So because we're riding on that sub-construction instead of at the substrate, we don't have to worry about shimming. We can create all sorts of kind of unique details and profiles to the building using that sub-construction. We have a lot more kind of freedom of movement with a rain screen than we do with, say, a bonded facade. We mitigate the risk of water infiltration, condensation, humidity, improve your drainage and drying, which extends the life of the facade, reduces maintenance costs. This is all a function of that cavity. The number one way that buildings are attacked is water infiltration, whether in a sinister way of like condensate kind of creeping in and out or hanging out in there, or say bulk water penetration gets in, and we're in the middle of winter in the Northeast region where during the day you get temperatures up in the 40s and 50s, and they bottom down into the 30s and 20s at night, where everything freezes, solidifies, and then causes cracking and spalling within your assembly. Basically, the essential takeaway is the number one way that the building is degrades over time is because of water infiltration. So if we eliminate most of that or provide a path out for water, that will extend the life of the facade significantly and mitigate the risk of wall assembly failures. Your improved energy and thermal efficiency is a function of your continuous outbound insulation and your thermally broken system. There are some air and moisture barriers that cannot be exposed to UV. They will actually degrade because your control layers are couched behind all these other layers of the assembly. They're protected. And we integrate really nicely with prefab and panelization because we're already working with a sub-construction system. All right, this should be kind of familiar to everyone. These are the control layers of every building. We're going to start at the substrate, and then we're going to work our way up to the exterior. And then we're going to walk back through those layers from the standpoint of a rain screen system. Your first three control layers: vapor, air, and water penetration control. I don't like to say barrier. The reason why is because the vapor barrier, for example, is installed on the warm side of the wall. If you live in a climate zone where you don't have a consistent warm side of the wall, for example, up in the Northeast, we have temperatures are very cold during the winter and very warm during the summer. Your warm side of the wall is going to flip-flop halfway through the year. We don't want to trap condensate anywhere in that assembly. We want to allow it to permeate to the dew point and exit. So usually we're talking one or two products that are combined and connected at the substrate to do this job. It's not going to be three separate components. Next up, we have our thermal barrier, and that's just kind of a fancy way of saying your continuous outbound insulation. Again, because we are talking about Rainscreens today, we are referring only to non-combustible insulation. We'll get to why when we get to the system layers. Finally, our durability and water shedding layer. This is an equally verbose way, overly verbose way, of referring to your facade. This is the aesthetic of the building. It should be beautiful. It should be skyline altering and win your firm loads and loads of awards. And also it should be your first line of defense. So it has to be durable. It has to meet performance requirements. It is the first protection for your building. All right, so we're backing it up to the substrate. System layer 1 of a Rainscreen is going to be your air and water resistive barrier. In this case, that gray stuff that you see on the sheathing is a thick mill fluid applied air and moisture barrier. That is enveloping the entire building, ideally. This is controlling moisture movement. We want any vapor or incidental moisture to find its way to wherever the dew point is. And we're controlling, in this case, where the dew point is. It's going to wind up in our cavity. System layer 2 is our subconstruction. The role of the subconstruction is threefold. The first is we want to create space for our outbound insulation. The second is we want to create additional space for our vent cavity outbound of that. And then third, and probably most importantly, is we need to be able to affix the facade elements and tie them back to structural. So when somebody asks how much our system is, I usually point them to something like this, because it could be the same exact subconstruction system that you're using, but if you're hanging terracotta 60 stories in the air in a hurricane zone, that's going to cost an awful lot more than if you were hanging metal panel 3 stories above the ground in an area where we don't expect a lot of deflection or wind loading. This is another thing that's going to dictate your cost, because it's going to dictate your bracket size, and that's your insulation. Usually the local energy code is going to have an R value that's telling you we need this many inches of mineral wool to achieve this R value, which means you're going to need a bracket of this length to house that mineral wool. And there's a few different ways that we can achieve that number. We may want to do it with 5 inches of insulation, for example, and use aluminum because it's less expensive. Or we may not have the lot line allowance for that, so we go to 4 inches of mineral wool and a stainless steel bracket. Or it could be that mineral wool, because at the moment we all know it's tough to get our hands on and it's extremely expensive. It might be that maybe we do want to go with less mineral wool and a more expensive bracket because it's cheaper to do that way. There's another option that's not on here. There are other metals out there, such as zinc, aluminum, magnesium coated, which clocks in at a comparable R value or effective R value for the wall, like stainless steel, but has a price point more comparable to aluminum. System layer 4 is going to be nothing. It's your vent cavity. It's an absence of material, and you can see that it's directly outbound of our insulation. It's at the face of our insulation, which is why, because we're where we are and we're expecting that chimney effect, that airflow pushing up through the vent cavity, that's what keeps our wall nice and dry. We don't want to be putting combustible insulation in this assembly. As far as the dimension for the vent cavity, so we're in the States, we do not have any sort of standard here. Typically, I see us deferring to the European standard, which is 20 to 50 millimeters. It's about 7/8 of an inch to 2 inches. I see around an inch on most projects. That said, Canada's done extensive testing, and they hold that 3/8 of an inch is sufficient to keep the wall dry. And finally, we have our facade or cladding. These are actually both Rainscreen systems. The curvy one is a render applied system. So you're going to have a plaster applied finish going over what is essentially behaving like a canvas. And all of our subconstruction layers are underneath, and it's vented out on the top and the bottom. So we do have airflow behind. The one adjacent is actually photovoltaic glass. And again, there is a Rainscreen system behind that as well. Now, let's say hypothetically you wanted a wood look for your building. There's a lot of different products that can give you that wood look, and not all of them are going to have the same performance levels from an impact standpoint, from a deflection standpoint, weathering, all of that. So you want to be mindful of, yes, we want to maintain our design intent, but also we need to tick all of these performance boxes. So we got to make sure we're picking the right thing to hold to that design intent. So just to recap, we have our air and weather resistive barrier. We have our subconstruction or furring, our outbound insulation, and our vent cavity, and then finally our facade. I know that was a lot of information. It's going to pop up over and over again, and you can always come to us offline if you need any clarification on any of that. We'll have time to answer some questions at the end. All right. For the building code, we're going to start with fire code because I like to get as controversial as possible as quickly as possible. Then we'll go through the energy code, sustainability, impact resistance, wind load resistance, and we'll close with structural stability. All right. These are multi-story fire tests. I think everyone is likely familiar with them. The NFPA 285 is the US standard, and the S134 is the Canadian standard. You'll notice there are a couple of differences between those two tests. For a start, the S134 includes fire breaks. The 285 does not. And the observation time differs across, as well as the burn times across both tests. The thing that stays the same is it's a 2-story mock wall. There's a burner on the header of the 1st-story window and in the center of the 1st-story room. They are ignited and extinguished at different times, and we want to make sure that we don't have excessive flame propagation into the 2nd floor. The one thing that I really want you to take home from this is these are assembly tests. They are not component tests. So if there is a manufacturer of, say, a foam plastic insulation that comes to you and says, we are non-combustible because we have our NFPA 285, be mindful that means that they are non-combustible when used in the exact manner and sequence that they were in the original test. If you're not using the same cladding, if you're using a different amount of insulation, if the sealants on the windows have changed from what they used in the test, you need to go to a qualified fire engineer to issue an engineering judgment to okay the change. So again, this is not a component test. There is another test for component combustibility. This is not it. The reason why it's relevant for Rainscreen is because, yes, we're dealing with non-combustible insulation, but you don't know, especially if you're using a Frankenstein system, if there's another component in there, like a passive house bracket that has plastic on it, or a combustible air and moisture barrier. There could be something else in there other than insulation that is combustible and will contribute to flame spread. So you want to make sure that you're looking at an assembly that has this test. I want to bring up some fire blocking requirements that have popped up in New York City. We are now required to put fire blocks around all openings, horizontally, approximately every 20 feet or every other floor line across the building, and vertically between occupancy units. What that fire break looks like is going to differ from assembly to assembly. There is no standard at this point. We're proposing details one at a time, piecemeal to the DOB. The reason why I want to bring it up here is because usually when something rolls out on the East Coast or the West Coast, it's adopted shortly thereafter by other municipalities. So just be on the lookout. There's likely to be some fire blocking changes in your city I would say within the next few years. Okay, energy code is going to be as a result of, or the requirements are going to be dictated by your local code. So it's going to differ from municipality to municipality. We have something called the New York Stretch up where I am. I know most major cities have their own stretch codes. Basically, that says, yeah, we see you and we'll raise you closer to passive house standards. Sustainability, there's a lot of different ways to source sustainable materials and kind of leave our planet better than we found it. EPDs are a good start. However, these are usually going to be component by component. So you want to kind of look at where you're sourcing everything. A B Corp is a little bit more of a cohesive, kind of holistic look. And they look not just at how you produce this individual bracket or rail, they actually look at your hiring practices. They look at your pay scale. They look at how you're sourcing your raw materials. What happens after the lifespan of the building? Are these things going to be landfilled somewhere and then seep into groundwater? They look at everything you do. So it does take longer to get a B Corp certification, but you're going to see a lot more of those labels, that certified B Corp label, popping up everywhere on food packaging, on material like furniture. You'll start to see that symbol more and more. Finally, local law 97. So this is actually, it's kind of, there's a battle going on in the courts in New York right now. We know that the number one way that we're contributing to our carbon footprint is with our existing building stock. So every city at this point is aiming to try and energy retrofit that existing building stock. The problem is a lot of building owners don't want to pay for it, understandably. So to kind of compel them to do so, we've passed something up here called Local Law 97, where they have an allotment for how much carbon emission a building can put out based on square footage. And that allotment reduces year over year. So the first year of the program, your building may be okay. And by the fifth or sixth year, it's not anymore. If you exceed that allotment, you have to pay a pretty punitive fine. So basically, the aim was to hit ownership in the wallet. So they feel more of a push to retrofit their buildings. Whether it's going to take effect, we don't know, because right now there's pushback on it. It was supposed to start this year. So more on that as this continues. Impact resistance, we have a few different tests for that. We have our hard body impact test. That's kind of a ballistics test where we drop a ball bearing repeatedly on the cladding and we kind of see the impact it makes. And then our soft body impact test is going to mimic a human body being propelled into the side of the building. The idea is we do not want to see additional piercing injury to the person when they strike the facade. So we swing that soft body pendulum. That's actually a opaque glass panel. We swing it into the side of the building. We don't want to see shards of glass being embedded in the pendulum. The Miami-Dade NOA, we rely on that a lot, even though we're not in some of us might be in Miami-Dade, but not all of us are. The NOA test is sometimes referred to as the missile impact test. We shoot a 2x4 out of a cannon. It's actually kind of a really cool test. And we see the force of the impact on the wall. So we want to make sure that it's not causing significant degradation to the cladding. We rely on this pretty heavily around the country now because the intent behind the test was actually not missile impact. It was to mimic projectiles being hurled at the building at a hurricane force wind gust. Throughout the country, we're seeing weather pattern changes as a result of climate change. We're seeing stronger storms in areas where we didn't previously see those. So more and more, we're seeing the Miami-Dade NOA being called out as a requirement throughout the country. The ISO 16933 bomb test, that's an explosives test. We take different weights of TNT and place them at different distances from our mock wall and then detonate them. We know that the force of the blast is going to cause hazard to human life and safety. We don't want for the cladding or the facade to degrade in such a way that it adds to that hazard. It's typically relied upon for transportation projects, high-profile projects, things like airports or subway stations, military bases, things like that. Wind load testing. So this is really what's going to determine your fastening schedule. This is what's going to tell you, hey, we're going to need X number of brackets and Y number linear feet of rail per square foot on this job. We create a vacuum seal around the wall and mimic wind loading in both directions, trying to force the panels into the building and winch them off the building. What we would like to see is things like deformation of studs, but the wall doesn't fail at like 240 miles an hour. We do not want to see fastener pull out and panels becoming shrapnel at 65 miles an hour. I think most major municipalities are going to have something very similar to the facade inspection and safety program. This one in particular is based in New York City and was previously known as Local Law 10 and then Local Law 11. A lot of people still refer to it that way. We have a lot of aging masonry in most cities, and the issue with that is the whatever wall ties are in there, if any, are corroded over time. We have a lot of cracking and spalling as a result of freeze-thaw cycles and water infiltration, and this causes a danger to bystanders and occupants alike. So we have a requirement in our municipality that every building 6 stories or higher needs a structural inspection of its facade, a probe of its facade, every 5 years to make sure that it's safe. All right, now we're going to get into the intersection between everything we just talked about and the Rainscreen system. This could very easily be my house. The shoemaker's children have no shoes. This is a residence that does not have continuous insulation. And as a result, we can see the guts of the building with a thermal camera. So every stud, the floor joists, the openings, we see everything. This is basically telling us that the only place where we have a thermal barrier is between the studs in the form of some sort of bad insulation. So we realize that when we have a building with a lot of thermal bridging, now if you translate this into a 180 unit apartment building, and you're trying to battle against this kind of level of thermal bridging to maintain a nice balmy 68 degrees in the unit when it's 110 degrees out, you can imagine that's going to use a considerable amount of energy to maintain that thermal comfort. So when it comes to Rainscreen, we like to do something called thermally breaking the system. So we do not want to carry that conductivity all the way through from the exterior to the interior. We know we're using subconstruction, so we're using a lot of metal. Metal is conductive, and we are potentially bridging through the continuous insulation that we're using. So by placing something like that little white rectangle on the back of the bracket, we are essentially breaking the bridge that would otherwise be formed by that bracket. I mentioned earlier, the zinc, aluminum, magnesium coated steel has a better level of conductivity or lack thereof than aluminum. It's more comparable to stainless steel, but the price point is a lot better. It also has some other qualities like self-healing when it scratches. It has it's a much lower rate of corrosion as well, so it's great for a nautical environment. And now we'll get into the combustibility or lack thereof of a Rainscreen system. So again, we are talking non-combustible insulation because we have that air gap directly outbound of the thermal layer. That said, we still want to have that assembly testing. And the reason why is because there could be another component, such as a thermal break that's made out of plastic. And we want to make sure that it doesn't contribute in any way to flame spread. Now, usually a component that small won't, but it's good to keep it buttoned up and make sure that you have the assembly test to ensure it doesn't. Here's an example of a fire block with a Rainscreen system. There's a few things that I want to point out here. The first is lamella. It's a kind of a dense block of mineral wool and that can act as blocking for an intumescent strip. An intumescent strip is a piece of fire-resistant material that when it heats up, when it comes into contact with, say, a flame, it will actually expand, which is handy dandy in a Rainscreen system because it will choke off the air cavity and block off that flame spread. We're no longer feeding oxygen to the fire, and it should stop at the block. I mentioned that we can have a lot of different types of cladding that achieve the same design intent. So I want to talk a little bit about sustainability with your cladding. First, full brick. Let's get right out in front of it. Is probably the least eco-friendly material that you can use to construct a building. It takes a tremendous amount of energy to power kilns to bake brick. Because it takes up so much space on a truck, we need significant more trucks to take it from the manufacturing plant to the job site. It's extremely heavy and labor intensive. We can get that same look with a thin brick, like a face brick or a cast brick. I know in the past, these have looked kind of tacky and they haven't performed very well. They've evolved considerably in the last, I would say, 3 to 5 years. They have a nice heavy texture on them, but they are lightweight. They are easy to install. You can pack a tremendous amount of square footage on a truck because they're small and lightweight. And it takes a lot less energy to manufacture them. So you can get that same timeless look of classic brick, but do it in an environmentally conscious way. Another sustainable cladding option is glass. The #1 ingredient in glass is sand, which we have plenty of. And we try to include recycled glass in the process as well. And then the big needle mover is if you're using a Rainscreen and you are extending the life of your facade because you've now mitigated moisture infiltration, that's going to extend the overall life of the building and extend the amount of time before we have to overclad or reclad it. That means hopefully decades longer before we have to tear everything down and landfill it. All right, we're going to kind of walk through what the spec process looks like right now versus what it could and should look like in light of everything that we just spoke about. I've been using these terms throughout the presentation: complete and incomplete, system and component. And I really want to kind of give you examples of what those look like and why you want to stick with the system approach. Because it's not just fire code that's critical. We want to be aware of the by others mentality with a component approach. And I'll show you what I mean by that. So this is a detail that's been put out from a sub-construction component manufacturer. And they may have a great component, but I don't know what everything else on this detail is, so I couldn't tell you. I want to point out the sheer volume of per architect callouts here. This is an effort, a conscious effort made by the manufacturer to basically say, if something goes wrong and our product is on the building, we are not going to own that. You specified us, it's your responsibility, which is not fair because they should be warrantying their own product. The other thing I want to point out is in callout #8, it says fastener spacing, edge distance, and open panel joint dimension per panel manufacturer. I don't like that. It should be per the sub-construction manufacturer. They should be determining if you are hanging a panel that is X pounds a square foot and you're going Y feet up in the air and expected in a zone 5, you're going to need this many brackets and this amount of spacing. They really should be determining the schedule because they're the ones responsible for carrying the load, but they're not even going to own that. This is one of my favorite details I've ever seen. It is a Z-girth that's been fastened into bad insulation. There is no sheathing. Therefore, there is no air and weather resistant barrier. There is no cladding. There is no cavity. It is somebody trying to sell you a Z-girth, and it's not physically possible. Here's another one from a facade panel manufacturer. Again, I just want to point out there's a lot of by others. There's stuff that's not even called out at all in the detail. And to be fair, a facade panel manufacturer is not looking to give you a rain screen. They're looking to give you an aesthetic option. So I understand that they're probably not going to want to own any of the engineering behind that, or potentially even know how to execute behind it. And the truth is, this detail could be awesome. This could be exactly what you need, but I have no idea what it is. I don't know what gauge it is. I don't know how big that rocket is. I don't know what it's made out of. We're showing tacons, I guess, going into masonry. Well, what if I'm going over studs? What kind of screw am I using to fasten this unknown piece of metal to the wall? So they want you to use their product, and it may look really pretty, but it's going to take a lot of work on your part to specify this safely, let alone up to code. This is actually a closed joint fiber cement Rainscreen system. They list their pricing, which is very nice. However, you'll see that there's a lot behind those panels and clips that says by others, which now creates a lot of question marks of how much this actually is going to cost you. The other thing I want to point out is because it's closed joint, it means that we're limited as to how we can run those panels. We certainly can't do a diagonal. If we start running them vertically, then we need to fur the wall out. And this is not produced in the States, so they're going based on metric boards, which creates some issues as far as spacing in a vertical installation. The other thing I want to point out is, yes, the cavity is very tight. There are actually continuous weave holes drilled in their hardware, so there is airflow back there. And they are kind of hanging their hat on the Canadian research that says 3/8 of an inch is sufficient. This is what happens when we use that component approach. And this is bad enough. Ownership was annoyed. They called in Morrison Hershfield to try and figure out why their brand new, freshly installed metal panel facade looked so unbelievably wonky. And they determined that it was because the improper detailing and transition between the subconstruction and the panels. Basically, we had movement somewhere in that wall that wasn't being accounted for by the subconstruction, and as a result, the panels started walking. We sometimes call that creep. Ownership wants it fixed. No one is going to pay for that. The panel person is going to point their finger at the subconstruction manufacturer, and the subconstruction manufacturer is going to point their finger right back at the panel manufacturer. And round and round they go. Nothing gets solved. This is where my blood pressure goes up. This was a natural stone panel that fell from the parapet on this building. It crash landed on somebody's balcony, took out the glass railing in the process. Thank God no one was hurt, but somebody very easily could have been. And we have an entire building that's been clad in this exact same system, which is worrisome to say the least. Again, Morrison Hershfield was called in to investigate, and they determined that there was a thermal mismatch between materials. There was improper movement at the substrate, which was then translating through to the panels, and then it ended up cracking and falling away from the anchor. There are a few things I want to point out here. First, if you are billing yourself as someone that can hang natural stone, best to understand it as a material. It's heavily porous. When it heats up during the day, it expands. When it cools down at night, it contracts again. So if you anchor into the back of it, it's going to stress fracture wherever the fasteners are. And that's why we have a tendency to use very thick panels usually and curve cut them. That looks very thin to me where it's laying on the patio. The other thing is I don't see anywhere in that rubble a safety mesh that was mounted to the back, which would have held the panel in place had it cracked. No one is going to take responsibility for this. Ideally, the entire building should come down. At a minimum, it needs to be probed and inspected. Nobody is going to want to pay for it. And they can hide behind each other. There are too many manufacturers to determine who's at fault. So let's look at the system approach. Names have been redacted, but everywhere you see the word system, it's coming from one source. There is nowhere for this manufacturer to hide. The only thing that they are not producing is that metal parapet piece, which can easily be built on site or bent on site. What I want to point out here is everything, including the air and water resistant barrier, is called out and coming from one source. It is designed to go together. In this case, we are looking at an opaque glass panel that is being hung on site. Everything from this attachment profile forward to the face of the glass is actually factory fabricated and shipped to the job site ready to hang. And this is what we can execute with one manufacturer using this system. It would be pretty challenging to create these kind of critical design details with multiple manufacturers from the engineering side, but you can definitely do it if you're working with one source. And a good manufacturer is going to have more than one aesthetic, and as a result, they're going to have multiple detail sets. So you have to make sure that you're looking at the correct details for the aesthetic that you're selecting. In this case, you can see that we've eliminated those two sets of rails. We're taking that same post-consumer recycled glass granulate carrier board, and this time we're fastening it raw to the T-profile, and we're applying a base coat mesh and finish. And this is what you can do with that project, that sort of system. So you can see we have these really cool radius walls. We can get a really tight radius with those boards. There's a little bit of play to them, or we can score them out if we're, kind of scooping around a tighter radius. And the nice thing is, because you're using one trade that's installing the whole system, ideally, they know where everything is. The challenges with the component approach are there's a lot of responsibility that gets foisted onto the shoulders of the architect, and it's very difficult to create a code compliant, cost efficient facade by using so many cooks in the kitchen. And it's just labor intensive on the architect's part. So anytime we specify anything, the fewer products and the fewer subcontractors we have involved, the less likely that we're going to have a design collision. It improves our constructability and project delivery considerably. Let's talk about what makes up the Rainscreen assembly and what that looks like. So the sum of the exterior cavity with the Rainscreen is your controllers, your component layers, and your vent cavity, right? So at a minimum, if you're using this Frankenstein or component approach, you're going to have your air and weather resistive barrier, your subconstruction, your continuous outbound insulation, your facade panel. So now each time you specify anything, whatever that product is, even if it's as simple as a fastener, you have to pull up specifications, product documentation, details, submittals, warranties, test reports, engineering judgments when relevant, and code approvals, POs, etc. for each of those components. That starts becoming an awful lot of paperwork. And there is a risk that somewhere in that paperwork is actually something that says that you cannot use this specific fastener with this specific facade panel in this climate zone, for example. So there's a lot of uncertainty here. It gets very convoluted, and it significantly impacts our ability to deliver on a project. Let's make it more realistic. Odds are very slim that we are designing homogeneous buildings. We're probably going to have at least two aesthetics on the building these days. So we already had this uncertainty and a lot of legwork going on and a lot of research going on with our single aesthetic, right? Well, let's say hypothetically, the glass manufacturer said you needed a peel and stick air and water resistive barrier behind their material. The plaster applied manufacturer said that you need to use a fluid applied air and water resistive barrier behind their material. What happens at the line where those two materials meet? We now have to do a pull test. We have to figure out whose membrane is lapping over whose. There's a lot of uncertainty there. And let's face it, when we get called in to look at a job that's failed, usually the place where we see the most amount of leaks happening are where two materials meet. It's at a termination. It's either the line between the masonry and the plaster applied finish, or at the window jambs. It's somewhere where one material is dying into another material. Rainscreen design, and really envelope design in general, is about managing risk while achieving your aesthetics and performance goals. So in this case, no matter how many skins you're using on the building, someone is taking responsibility for the chassis of the building. They are taking responsibility for all of your control and system layers. And then you can hang one of their aesthetics, or you could say, we don't like your aesthetics, we prefer this specific aesthetic, and they can run the load table and run the calculations to hang that third-party aesthetic and do so without disrupting the control layers underneath. Simple to say, using one source significantly reduces your risk and increases the level of performance of the building. You have one warranty from a single supplier. You have assured compatibility of components. Your assembly is fully tested for fire, structural, thermal, wind load, all that good stuff. You have weather tight transitions because we're using a single air and water resistive barrier for the entire building. Your by others design collisions are avoided because they're not by others anymore, and you have one phone call to make. All right, those are our learning objectives, all complete. You guys did great. I'm gonna call up Brock and ask him to facilitate our Q&A, please.
Awesome. All right, Brock, if you want to turn your video on, you will pop up as well. And looks like we do have a few questions. Just gonna send a reminder to everyone, if you would like to submit a question now, feel free to do so. You can also raise your hand and ask a question out loud if you would like, so that we can talk about it out loud. So feel free to do that. I'll keep my eyes on. Oh, looks like we got, oh, they put it back down. All right, well, I'll keep my eyes out. If you want to raise your hand, feel free to. Brock, do you want to read out the questions, or do you want me to?
Sure. No, I don't mind.
Okay.
So, Kate, can you discuss and elaborate on how you address the new energy code requirement for continuous insulation, XPS, for instance, to prevent thermal breaks in the building envelope?
That's an excellent question. Okay, so first thing I want to point out is we're not going to use XPS with a Rainscreen system because XPS is a foam plastic. The other thing I want to point out is if we're doing a non-Rainscreen system, for example, like an EAF system, and we're looking at XPS, most people are coming away from XPS foam and moving more towards like a GPS foam, which has a comparable R value, but a lower price point. As a result of the Paris Accords, the amount of refrigerant that's or a blowing agent that's used for producing XPS, extruded polystyrene boards, had to be reduced, which increases the costs to make those boards. So most manufacturers are pointing you in the direction of GPS at this point if they need to budget create a friendlier, a more budget friendly option for their wall assembly. Again, we're not going to be using XPS behind a Rainscreen system because we have that air gap. But generally speaking, if we're talking about achieving the energy code or exceeding the energy code, we want to make sure our subconstruction is thermally broken, and we want to create as few connection points from the exterior to the interior as possible through that thermal barrier, which is why it's nicer to use, say, a bracket and rail system as opposed to rails continuously running down the side.
Excellent. Thank you. Next question is from Greg. So in the example where structural movement was found to have propagated into the Rainscreen, would there have been a benefit to a complete systems approach?
Yeah, ideally they would have, if it was a complete system, we would have had the engineering behind it to account for that movement and hopefully prevent that from happening. But hypothetically, if the engineering had failed and something had fallen off the building, which odds are slim that it would happen if it's a full assembly, but if it does, the manufacturer is left holding the bag and not the architect or the engineer. They're the one that created the system. There's nowhere for them to hide in that wall section.
Right. Here's another one, Kate. On public works, when 3 manufacturers are required, what impact does this have on your systems approach?
That is, and Brock, I see you making face. That is like our nightmare right now, honestly. So I mentioned at the beginning, because the Rainscreen system is, as a whole system, falls in different divisions, it's kind of difficult to specify our approach because we're owning the whole building and nobody really has a comparable, like an either or to that. So they would have to break out our lovely full system into components and specify it that way. So they would, for example, take our air and water resistant barrier air seal and specify it next to a Henry Blueskin or something like that. And then they would take our bracket system and specify it next to another subconstruction manufacturer. that's one way I've seen it done. The other way is some municipalities will let you get around it with like an or equal or a performance spec that like only we can meet by writing it a certain way. I have no good answer, honestly. I can just
Yeah,
tell
no,
you what I've seen.
it's a tough one. Let's see, Kate, can we create, this is from Steve. Can we create a spec for a Rainscreen system? It's up to us. How does this, can we create a spec for a Rainscreen system? It's up to us. How does this option work? Not sure I completely am relaying that properly, but that's
I
what's
feel like
written.
it's along the same lines as the last question, kind of.
Yeah,
We do have a specification that you can pull off our website for our system, but
yeah.
usually you're going to have to kind of cannibalize it when you
Uh,
get into it.
Here's a really good one from Paul. So what's the best approach? Having the drainage plane behind the veneer or back behind the insulation?
I think it depends. Um, if you have like a closed system, like an EAF system, like a StoTherm CI kind of thing, then it's okay to have that capillary leak function way back behind at the substrate because we're really not expecting any tremendous amounts of moisture to like find their way back there.
Mm,
It's pretty tightly sealed up. If you're going to a rain screen system, you want all that airflow, then we definitely want it outbound of the thermal barrier because that kind of intentionally places the dew point of the wall in the air gap.
right.
It really is, it's two different ways of designing the building. If you want my personal opinion, I am partial to rain screen. I'm obviously not objective.
And Kate, let me rephrase this. I think the question was specific to all Rainscreen systems. Is it better to have the water
Okay,
drainage plane back behind, behind the front panel or behind the insulation, kind of running down the air barrier?
behind the front panel,
Right.
outbound of the insulation, because that's where we're placing the dew point.
Right. I agree with that.
Mhm.
I'm going to ask one from my library of most popular questions that get asked. I get asked a lot, can foam plastics be used in Rainscreen systems?
Never. I mean, they can't, I'm not the insulation police. I can't possibly travel from job site to job site and slap people on the wrist when they try to put foam plastic in a rain screen. However, please don't. You have a lot of airflow going on in that vent cavity. It's designed to do that. That's the whole point. If you wouldn't line the walls of your fireplace with it, then you should not be using it in a rain screen system. It will ride up the side of the building very, very quickly. We've seen that tragedy happen far too many times. We recently saw it again in Spain. There was Grenfell Tower. There was one in Dubai where there was something combustible adjacent to a sizable air gap, and it just right up the side of the building. It's extremely dangerous, so please don't do it.
Gotcha. And the last question, I think the last one we have time for, at what stage do I engage my Rainscreen product rep?
Early and often. As early as possible. I would far rather have a conversation with somebody during the schematics phase and you give me a phone call 3 years later and say, hey, the project's dead. That's not a waste of my time at all. I'm a rain screen nerd. I think we're both those building science nerds there. We want to have these conversations. I would much rather that than what I've been getting, which is, oh man, if only we talked to you 6 months ago. We're
Yeah,
in the middle of construction right now. We could have used you. Call us whenever. We're happy to chit chat.
sure. Bo, are we out of time?
We've got about 1 minute left. So yeah, I think we should probably call it. I do see there was one or two more questions that popped in. But yeah, I just want to say thank you, Kate and Brock, for joining today. Kate, that was a really awesome presentation. And thank you so much to everyone in the audience for asking such great questions and for engaging with us. We really appreciate it. Before I jump out of the webinar, if there are any of the links that you wanted to grab out of the chat to bookmark those for later, now's a good time to grab some of those links. You can head to Acelab, get in touch with Kate and Brock directly. There's also a meeting link for Helen to get in touch with her if you want more of a deep dive on using Acelab for building product research. All right. with that, we're at 2 p.m. So we'll let everyone go for the day. Hope everyone has a great rest of the day. And thanks again, Kate and Brock.
Thank
Thank
you
you so
both.
much.
All right, bye.
Bye.